Hello everybody. Today we will talk about quantum amplitude amplification. We know that in quantum systems, when we try to measure the quantum states, the measurement results are probabilistic. What we want to do is that we want to amplify the correct answers and we want to suppress all other answers. So what is our goal? Our goal in amplitude amplification is that the amplitude of the correct answer should be as large as possible and the amplitude of the wrong answer should be as small as possible. So what is the first step in amplitude amplification? We will create an equal superposition of all basis states. So if we initialize the quantum state with all zeros and we apply it through the Hadamard gates, and the output will be an equal superposition of all the basis states. And that is quite clear from this graph, where Cx is the representation of the quantum amplitudes. All the states have got the same amplitudes and we want to amplify the amplitude of the target state, which is ket y. We want to amplify the amplitude of ket y as large as possible so that there is a very high probability that we get the correct state as the measurement output. Now what is the next step in amplitude amplification? We apply a phase flip oracle for the target state y. So what this phase flip oracle will do? Phase flip oracle will give a minus sign, will flip the target state. That means it will give the minus sign to the amplitude of the target state. So this is the target state with negative sign. After the phase flip oracle, we try to apply a diffusion operator. Now, what is the job of the diffusion operator? It flips all amplitudes over the mean amplitude. We'll try to see what is the meaning of the flipping of all the amplitudes over the mean, and it is also known as inversion about the mean. We will try to look the meaning of inversion about the mean in classical terms with the help of an example and in quantum terms. Now, this is the graph before we apply the diffusion operator. So we calculate the mean of all the states. So mean of all the states is not the top amplitude but little bit lesser because there is a negative amplitude of the target y state. But this graph is after the diffusion operator. So what the diffusion operator has done, it has flipped the target state amplitude and it has tried to amplify it. And secondly, it has also tried to suppress other amplitudes so that the chances of getting this amplified target state as the measurement output becomes as high as possible. So let us try to understand the meaning of inversion around the mean with the help of an example. Let us consider a set of real numbers. The mean is given by m by the summation of all the numbers and dividing by the total number of numbers. So on the real number axis, m is the mean and mean will be some distance away from a number of choice, let's say x. And we want to know that what we get when we invert around the mean. So therefore, when we do the inversion around the mean, so we reach to x dash, which is also equidistant from m. So that means x dash minus m is the distance of x dash from M, and x is a point x minus M away from mean. And if you try to calculate for x dash, you will find that it comes out to be 2 times mean minus x. Now this is known as inversion around the mean. We can extend the same approach to quantum computations. So let's look at the diffusion operator doing the job of inversion around the mean. So diffusion operator is basically a unitary operator. It is given by twice the outer product of a quantum state S minus the identity matrix. What is ket S? Ket S is actually the equal superposition of all the basis states. And we have diffusion operator D, and we want to know the action of diffusion operator D on an arbitrary state psi. We will also geometrically visualize what is happening by considering all these states. So our ket psi, which is an arbitrary state, is given by alpha ket psi plus beta ket y. So ket psi will have some component of psi along ket S and some component of psi along y. What is y? Which is everything but S. So therefore, y will have everything but not S. So therefore, if you take the inner product of S and y, it will come out to be 0. Now we apply the diffusion operator to this arbitrary state ket psi. So if you do this maths, you will find that the inner product of S and psi is alpha basically. So the application of diffusion operator on psi is actually equal to alpha ket S minus beta ket y. So therefore, non-S component gets the phase flip after the diffusion operator. Right? Now we can visualize the action of diffusion operator, that is 2 outer product of S minus I on ket psi geometrically. So let's try to understand the geometric visualization. We have two states. We have rather orthonormal basis x's. One is ket W and ket V. Ket W is our target state. Ket V is everything but W state. We have this equal superposition state ket S. So target state is ket W and everything else state is ket V. And we can also plot ket S on these axes, that is ket W and ket V axis. As I have just discussed, ket S is the equal superposition of all the states, which includes ket V and ket W. Now ket S has lot more overlap with V than W. So that is why this ket S is more close towards V, because ket W is the target state, but ket V is the combination of all other states. So ket S, being the equal superposition state, will have the contribution, will have more overlap towards V rather than W. But our target is to take the measurement as close as possible towards W. So let's see how it is possible. Now if we start with some state ket psi, so this is our ket psi. So let's start from here. So if we start with some state psi and we apply the diffusion operator, the component of psi which is not along the S axis, that component will be flipped. Therefore, we are going to get mirrored over the S axis. So this component, this green component, will get mirrored across the S axis. So we reach to this point after the diffusion operator application onto the arbitrary state ket psi. So from the visualization, it appears that the diffusion operator is quite useful, because let's say we want to measure target state W and we have an arbitrary state ket psi beforehand, and of course we will apply diffusion operator on this ket psi, which inverts ket psi over ket S. Hence the overlap of W with our state has greatly increased and overlap with V has greatly decreased. So what is the meaning? When it was S, the overlap of S with W was minimal, but overlap of S with V was maximal. But considering an arbitrary state ket psi, when we apply the diffusion operator, it goes to this point where the overlap with W state has significantly increased, whereas the overlap with V state has significantly decreased. So therefore, the application of the diffusion operator is taking the arbitrary state as close as possible to the target state, and that is the geometric visualization, but actually it is inversion about the mean. That means it is trying to amplify the amplitude, the quantum amplitude of the target state, and it is trying to suppress the amplitudes of the other states. Now we can construct D also. Let us see how to construct the diffusion operator. We know that the diffusion operator actually is given by twice the outer product of S minus I, but we can start a bit simpler. We can start with an all zero state. So that means in this case, to start with, our diffusion operator is the outer product of zero states twice the outer product of the zero state minus identity matrix. So the diffusion operator flips the phase of everything but the all zero state, or flips the phase of only ket 00 state. So see, whether it flips the phase of everything but the all zero state or only the all zero state. Since in quantum systems we worry more about the relative phase rather than the global phase. So whether it is the phase of the ket 00 state being flipped or the phase of everything else but ket 00 state. So it means it has got the same meaning, because what ultimately matters is the relative phase and not the global phase. So this sounds like a phase flip oracle for the target state ket 00. So we know that how the phase flip oracle can be implemented using the poly X gates and the control Z gate. But the full operator has the outer product of S rather than ket 00 state. So the full operator is twice the outer product of S minus identity matrix. So how can we reach from the all zero states to the outer product of the to the full operator stage. Now that can be done by applying the Hadamard gates onto the all zero state from the left and from the right. And if you solve this equation, you will find that this equation will come out to be the full diffusion operator. And this is how this portion up to the X gates, this in between dots are representing the control set gate. This portion is the phase flip oracle, and the Hadamard gate on the left and the Hadamard gate on the right actually provides the diffusion operator, which is basically doing the amplitude amplification. Thank you very much.